Hello and welcome to Autoinform online magazine Diagnostic Workshop. My name is Frank Massey. In this edition we're going to take a look at digital air mass meter evaluation. Traditionally that's been a challenge because we had to mix digital and analogue signal evaluation when looking at field trim. We overcame this initially with the use of a current clamp, and more recently we now have some software capability of converting a digital signal into an analogue representation. So I'd like to demonstrate both the tools, the connectivity, and the way in which we can now choose each of those options when evaluating a digital air mass meter. I'd also, as part of the practical presentation, like to show how this is achieved when comparing it with a wideband lambda sensor. So first of all, what I'd like to do is demonstrate and show you how we care for our leads, and then demonstrate the connectivity to the vehicle which we're now going to use. The lead stand in effect allows the leads to be stored with minimal stress. One of the problems with lead failure and poor connectivity often is that the leads are stressed either by bending, curling them, or storing them inappropriately. So wherever possible we try to keep the leads as free and natural as possible. I've connected two oscilloscope probes, voltage probe leads already. We're going to take a further two connections when measuring current, and we overcame the issue of discrete current measurement with a very sensitive 0 to 450 milliamp inductive clamp. We're going to use this device to convert a current measurement from the digital air mass meter, and we're also going to use the second device, identical to this, to measure the current flow through the signal wire of a 5-wire wideband lambda sensor. And then we can compare both the original digital output, we can then look at the conversion through a software analysis into an analog representation, and we can finally compare it with current flow. And then we're going to do a quick fuel trim analysis comparing the activity of the air mass meter against the response of the broadband sensor, the wideband sensor, in the pre-cat exhaust location. So first of all, let me connect first of all to the digital signal cable from the air mass meter. So we're going to look at just pure voltage as a digital representation. The functionality of this particular sensor is one whereby the frequency of the signal will increase with an increase in air mass measurement, and that in itself is a fairly simple and very easy measurement to make. And I think it's fair to say there's actually another way of evaluating air mass meters, and that's down the serial route. You can drive the vehicle, monitor live data, and look at the representation of calculated air mass, which is usually in kilograms per second. It may be of use to you that you can calculate or predict the correct value for an air mass meter by multiplying the brake horsepower of the engine by 0.8, and that should represent the maximum air mass signal calculation on full load. So having said that, let's take a look at how we're going to connect to this particular vehicle. First thing we need is one of our voltage probes, and I'm going to insert this in the signal cable by inserting the probe in effect alongside the cable down the rubber boot on the back of the connection pin. That should produce a good robust connection with the connection terminal inside the socket. That's the first connection. I'd like to do what we call a floating measurement. I've already checked that the earth reference against battery negative terminal is indeed within specification. That's quite important. I would also now like to take a second probe and use this as a floating ground reference. So I'm going to actually insert this in the center pin. It's a little bit dark, so I think we'll have a little bit more light. And lighting is one of these issues whereby we've tried a number of things in the past, and we found this type of light casts a fairly neutral, shadow-free light. We diagnostics obviously want to see wire colour, connectivity, as well as illuminate the area. So we found this one of the better options when conducting testing. Right, the ground connection is in the middle pin. I'm obviously conscious that neither of these probes will touch each other, and I think that is on the pin. So we now have a signal cable connection and a ground connection. We now can connect our voltage probe. The primary channel, channel 1, blue, I'm going to use as the signal cable, which should have a digital signal. I'm going to use the ground reference with the preferred short ground lead. That's the first priority. The next priority is now to set that channel up. It's a 5 volt signal, or it's based over a 5 volt range. So I'm going to change channel 1 from 50 volts, as it is now, to 10 volts. That gives us a reasonable image size on the screen. Now, I also want to request a measurement from this signal. It's a digital signal, it has a frequency. So I'm going to use the measurement function on channel A, and we want to measure frequency, so I'm going to select frequency and apply it. So we now have at the bottom of the screen the frequency measured from that component. That's the channel 1 setup, 10 volts, measuring frequency in a traditional manner. The next connection, I'm going to use channel 2, the red channel, on the same signal cable. So I'm going to connect the second probe around the actual needle, which is inserted in the pin in the socket, and share the same ground reference. So we now have 2 signal connections, one providing the digital signal. The second probe now is the new feature I want to demonstrate, which is the conversion of that digital signal into an analog representation, and that is done through the software on screen. Channel 2 at the moment is set for voltage. I'm going to select the probe menu with the coupling, which is normally DC and AC, and if we open that particular function, you can see a new feature, frequency. If I then select frequency, I can now select the range, which has now been converted to a frequency reference, and if I open that box up, you can see there's an automatic function, a 0 to 2 kilohertz, 0 to 2000 hertz, and 0 to 20,000 hertz. This particular device operates approximately from 1000 hertz at idle to about 9600. So let's say it's 0 to 10,000. So it's going to be appropriate to set the 0 to 20 range. So the second channel, which we've set up, will now convert that digital signal to an analog representation. That's the first 2 channels we've set up. So I think we can demonstrate that now. We need to start the vehicle, demonstrate that measurement before we add current as the third option. So we're looking at voltage and frequency, we're looking at conversion to an analog signal, and then we're going to add current measurement. So if we can start the vehicle. Now this demonstrates the problem very clearly, that we have a frequency, a very high frequency, or a reasonably high frequency, and we now have the analog representation as a frequency conversion. We need to examine that signal in some detail, so we need to divide the time in such a way we can actually examine the signal in some detail. So I'm going to choose quite a short time base of 500 microseconds, that's half of 1 millionth of a second per division. And you can now see a very clear, easy to understand representation of the output signal from that air mass meter, and we also have the relevant frequency measurements as a digital signal. All of that is fine, but we can't mix those 2 signals in a format to do field trim analysis. The purpose of this demonstration is you can see that that signal has been converted very accurately to an analog representation. I'm going to leave that connected, although we're now not going to concentrate on that. We're now going to concentrate on our ability to view the performance of this air mass meter as an analog signal. So I'm going to select an appropriate time, which is 20 to 50 seconds across the screen. So I'm going to choose 2 seconds per division. It's a 10 grid screen. That gives us 20 seconds sweep time to conduct a wide open throttle test. So just before we do that, you can see that that signal now has become compressed into an envelope whereby we can no longer evaluate that accurately. I'm going to ask for a wide open throttle in a moment. And if we give wide open throttle, please. Now this is an excellent way of actually proving this very point. That analog image can now be very clearly understood, whereas a digital image would be impossible to convert into such a meaningful message. Happy with that setup? Let's now add a third input, which is current, and let's compare the functionality of current measurement from the air mass meter with the two options which we now have. First of all, we need to switch the clamp on. It's a BNC connection with an inductive probe, which is directional sensitive. The direction arrow goes in the direction of the device. The device is the air mass meter, and we measure current on the power supply to the air mass meter, not the signal cable. So first of all, let's connect this to the scope. And connect this probe direction to the device around the power cable. The next thing we need to assess or estimate is the attenuation or sensitivity of the clamp. Now we've found from research and development and some experience that a 2-volt range gives us enough image size for the entire output range of the air mass meter. The conversion rate is every 10 millivolts is 1 milliamp. So 2 volts becomes 200 milliamps of current flow. So I'm going to now select the green channel, channel 3, at a 2-volt range. And I'd like to separate some of these images, so I'm going to bring the scaling down so that you can observe the image both in current, green, conversion from a digital signal to an analog signal in red. I'm going to move the blue digital image out of the way, leave it there for reference, but what I'd really like you to view and see is the performance of these two. Now I think it may be easier if I actually bring the baseline down on both of those channels. So what I'd like to do to give you an accurate representation, I've set a theoretical baseline on both current and analog representation. And I'd now like you to do another full throttle test for us, please. And if you can switch off. I'll just capture that. Now, I think it's very clear here where the benefits of an analog representation outweigh a digital representation. In effect, what's been embedded or hidden in that signal now has been extracted in two ways. We've extracted it as a software manipulation, which is the red image. So there's been a conversion from that frequency to an analog image on the red channel, channel 2. And there's been a conversion from the current flow through the air mass meter to an analog image in green. And I think you'll agree, I have no intention of moving those, I think you'll agree that the profile or the similarity in profile is extremely accurate one. So I'm quite pleased in using either of those options. This now puts us in a position where we can compare the response of the air mass meter, a digital air mass meter, with the wideband or broadband lambda sensor. And one way we can evaluate that component is also to measure current. It actually does use current as a control function. So I'm going to use a second inductive clamp of the same range, effectively 0 to 450 milliamps, same connectivity, BNC connector, inductive probe, directional. The direction of the arrow is towards the device. The device now is the lambda sensor. Both probes connected. So this probe now goes on the signal cable of the lambda sensor, which is the red or pink cable, with the arrow in the direction of the device, which is to my left. Goes completely around the cable, making sure the jaws are completely closed. Now that the connection has been achieved, we need to convert the range on the scope to convert current into an analog image. And we have found that a range of around 200 millivolts should produce a reasonably responsive signal size. So I'm going to change channel 4 to 200 millivolts. That gives us a 20 milliamp range. I'm only expecting about 5 milliamp deviation, so I may actually change that to 100 millivolts, which is a 10 milliamp range. Bear in mind, this evaluation is done with simulated full load. If you were to do this test on the road, you might expect a bigger current flow through the broadband or wideband lambda sensor than we actually achieve here. And indeed, you may even see a bigger image size both on current as well. So if you kindly start up to begin with. Start the scope running. I just want to make sure we have an image. Now, the lambda sensor, the wideband broadband sensor, should, if the fuel ratio is at lambda 1, stoichiometric, we should have a 0 current flow through the signal cable. And if we observe that reading, it is at 0. A rich deviation will give us a negative current flow, and a lean deviation will give us a positive current flow. Perfect fuel, lambda 1, should be 0. So kindly, if you give it a full throttle response. And off, please. And once again, I'll capture that event. Now I think this very, very clearly. Let's make sure we capture the event. Go back one frame. I think this very clearly now demonstrates where current has a unique advantage, both in air mass meter, digital air mass meter evaluation, and it actually is the correct way of measuring and evaluating broadband wideband sensors. We can clearly see that the on-load event is represented by a rich deviation, negative current, and the throttle off produces obviously a lot of oxygen in the exhaust stream with no fuel, a excess oxygen deviation. In the positive current, we can see that negative or 0 is here, and we can now evaluate how much current is flowing. We've actually flowed 40 millivolts, which is 4 milliamps of current with a considerable lean deviation. That's only part of the evaluation. What we need to do is use this zoom feature and take a look at this part of the signal in some detail, because I want to try and evaluate the response time between the load request, and the load request is at the point where an increase in airflow is detected. At that point there, you can see an increase in airflow, and the point at which we get a rich deviation. Now, characteristic of a broadband wideband sensor is that we don't get an over-rich deviation. It's quite a subtle deviation when done in the workshop statically. So I'm going to take or claim the first deviation as that point there. And by evaluating the time between those two cursors from the point of request to the point of change in oxygen content, if you like, in the exhaust stream, in this case it's a rich deviation, rich current deviation negative, we could evaluate the efficiency of the fueling, and that figure should be 200 milliseconds or less. Now, this is a fairly high performance engine. There is actually some performance software in this as well. So the response of this may be a little bit more aggressive, more quickly than would perhaps on a smaller engine, perhaps a 3-cylinder engine. But the figure is nonetheless still quite an accurate one. So 200 milliseconds to around 300 milliseconds of response time is an excellent representation of the ability of this injection system to deliver fuel into the cylinder, and also reflects how efficiently that fuel and air has been used, combusted. And of course, once we lift off, fuel is turned off and we get this lean deviation. So we can also compare the negative part of that event by looking at when the lambda, when in actual fact, if we're being strictly accurate, it started to correct itself at that point, and the air mass meter started to reduce its flow in air. And once again, we can see that the reaction on the lean or fuel off cycle can also represent very accurately the response, the differential between measuring air and comparing the reaction in the exhaust stream of oxygen content. So we're back in business. This is the way we did fuel trim evaluation. This is on the load cycle, and of course we can evaluate this at all different ranges: natural idle, cruise, wide open throttle, and we could of course actually reproduce this test actually on the road. We'd need to use extension leads from the device into the car, obviously put the scope and the laptop on the passenger seat and take a co-pilot with us. But we can achieve some very, very accurate results on real-time fueling analysis based on conversion of a digital air mass meter and current measurement through the wideband broadband sensor. And this now puts us in a position where we can now continue with the traditional means of testing with the new generation sensors, and indeed any component which is driven digitally now gives us the opportunity of measuring an analogue representation of that device. So it opens up a whole range of new capabilities from that type of signal analysis. That concludes the presentation. I hope you've found this additionally interesting on top of some of the presentations we've done in the past relative to digital air mass meters. It gives us this extra option of measurement. So I'd like to thank you for joining me, and I look forward to seeing you next time.